There we go. Okay. Hello, everybody who's watching over the internet later. So we're just finishing lecture 17 today, and that's all we're going to be doing. So this is lecture 17, but it was started on the previous video. So sorry, I'm talking to them, but they have to know. So anyway, I'm going to turn these lights off so you can all see this, and then we're going to fast forward to where we're supposed to be today. Okay. Blah, 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 blah. And where were we in the lecture packet? We were getting through, we were just getting through to, we got through all this, remember that? Yeah? What?
Did you take roll?
No, I didn't. Let me take roll. That's a good point. That's a good point. So let me take roll really quick. Okay, it is for. Okay, April. Oh man, this is a terrible pencil. Okay, 4, 6, and then Clarissa's excuse today. Oh, and Alex Trevino, I have your I have stuff right back for you. Sorry. There you go. Did Kayla come in? No. Okay. So Samantha Lugo's here. Eliana's here. Samantha Rodarte's here. Francis. Not here. That's unusual. Hayden's here. Gavin, you're here. And Amanda's here. Alex Cox is here. Alex Trevino's here. Bree is here. Valerie's here. Kayla's not here. And then Julia's are here. And Tim is here. And Jaden's here. And Colton's here. And Steve is here. And Gus, Kaya, Liam, and Natalia. All right. Gotcha. Now, we were just getting into. So it's kind of funny because we've been going over all this stuff, for the last 2 days, and you remember all this, right? That, right? What is that about? The people on the Coriolis force, right? I'm telling you all, that's just really important because it doesn't stop. It keeps going when we talk about ocean circulation too. It comes up a lot, so you got to make sure you know this Coriolis force. So in the northern hemisphere, it causes a deflection to the right. In the southern hemisphere, it causes deflection to the. Okay, so a fluid is going to try to move in a straight line. A fluid's going to try to move in a straight line, whether it's water, ocean, or it's atmosphere. It's going to try to move in a straight line, but it's going to get deflected to the right in the north, deflected to the south, left in the south. Gosh. Okay, and then and that's Coriolis force, right? And that happens with whether you're talking about ocean currents or you're talking about air currents. It happens with both. Okay, so it's very important you remember that. All right, so actually it's kind of funny because everything that we've been talking about the last 2 days, it's all just kind of leading up for you to understand these global circulation belts. So today's lecture is like everything so far for air circulation has just been kind of not review, but been kind of like getting you prepped so that you can understand these circulation belts that occur over Earth's surface, okay? And how they migrate and they change over the seasons, because that's going to be the main reason that we're learning about the atmosphere right now, is because these things have a big effect upon ocean currents. So we have to know them to understand the ocean patterns in ocean currents. Okay. All right. So the Earth's global wind belts and the global circulation pattern. So we're on number 13. That's right. Okay. So the first thing here you got to know is a little something called the ITCZ. And that stands for Intertropical Convergence Zone. Intertropical Convergence Zone. So I'm not going to ask you what it stands for on the test, but if you just know ITCZ, honestly, to be quite honest with you, I sometimes forget what it stands for, but I know what it is. So the ITCZ is Intertropical Convergence Zone. And what it is it is a belt around the Earth of high temperatures in which the air is rising. Okay, so it's, generally speaking, it hangs out and it actually migrates, okay? The ITCZ migrates. So it's not always in the same spot, but generally it hangs around the equator. So generally speaking, it hangs out around the equator. But it's going to move north and south a little bit, kind of following the sun, kind of following like, because remember, on the summer solstice, the sun is directly overhead at which point? What line of latitude? The sun is directly overhead at the summer solstice at what line of latitude? Did I hear that? The tropic of, well, it doesn't matter, 23.5 degrees north, right? 23.5, so Tropic of Cancer. So it's hanging out right above the 23.5, so right above the North Tropic, okay? So the ITCZ is actually going to follow it, and it's going to migrate north it's going to migrate to the north during the summer solstice and during the summer, and then it's going to migrate down to the south during the summer, the basically our winter solstice, the southern summer solstice, right? You all know that it's summer. When it's our winter, it's their summer, right, in the south. So it's flipped, right? The seasons are flipped down there. But it's going to migrate, when we get into our winter, it's going to migrate to the south, okay? So the ITCZ is going to be following that, all right? So it migrates, but it basically hangs out somewhere between the tropics, okay? And it's just this band of basically very hot air that's rising, and it's hot because you're getting a lot of sunshine there, directly above what's called the subsolar point, where the sun is directly overhead. Okay, you're getting the most direct sunshine, and it's really hot, and the air rises. And what happens to air when it rises? It cools off, and it cools off due to adiabatic. Oh my gosh, that's so good. You even knew the $100 word, adiabatic. It cools off due to adiabatic cooling, right? Depressurization, cooling. So it's going to depressurize, and then it's going to, when it depressurizes and it cools off, what is it going to do? What's that? Condensate. It's going to condense. There's going to be condensation and precipitation, and you get heavy, heavy, heavy rainfall, right? Has anyone ever heard of a monsoon? Right? The monsoon season, or has anyone ever lived in a country or been in a country that has a rainy season? We kind of have a little taste of it, but not because we're close to the tropics. We have a little taste of it here in Corpus. But has anyone actually lived in a place? You have
South Korea.
Yeah. Okay.
So they had these times where it would just
dump, right?
Yeah, dump.
Yeah. Right. And like I was saying, when I was in Africa, in Malawi, there was a rainy season, and I mean it was bone dry during the dry season, bone dry, no precipitation, and then a rainy season, it was a monsoon, right? Every day rain, and heavy rains, right? So that's what happens when that Mr. ITCZ gets right up on top of you. Then it's monsoon season, okay? Because it's heavy, heavy rains. So this creates a lot of precipitation around the equator. All right, so if you look at the Earth, you'll notice that the Earth actually kind of wears like a belt. It kind of has a belt like this, and it has a belt of clouds. Do you all see that? Do you see its belt of clouds? So it has a belt of clouds. The Earth wears a belt of clouds, and that belt is actually, you're literally looking at the ITCZ. So that's the ITCZ. That's the band of hot air that's rising, then it cools off and it creates the precipitation. Okay, so why is there a lot of precipitation along the ITCZ? It's because the air is hot, it convects, it rises, and then it cools off and condenses due to adiabatic cooling. I'm sorry, that's a lot to put in one sentence right there in that little space. I'm paring this down. I know it doesn't affect you, but in the future I'm cutting stuff out. All right, Corpus Christi. Do we have any rainforests here in Texas? Do we have like a rainforest? No, we don't have a rainforest here. Okay. Can anyone think of like a place that has a rainforest? Has anyone ever been to a rainforest before? Like a real rainforest? Do we have a rainforest in America?
Washington.
We do actually, yeah. We actually have a rainforest in Washington, but there's a separate reason that there's a rainforest there. But you have to have a lot of like constant precipitation for that. That's actually due to the location of the Cascade Mountains and rain shadow effects. But so we do. But most rainforests are actually, look where most rainforests are. Now we do have a little rainforest right here in the North Pacific Northwest. But look where most of the rainforest is. Now, reason that you don't see anything there in North America because these are specifically tropical rainforests. Okay, but a lot of this area is covered with rainforest, right? You see quite a bit of it is covered with rainforest. So why is that? It's because the ITCZ is spending a lot of time around the equator. Okay, because it hangs out. Its normal haunt is the equator. Okay, it does migrate north and south with the seasons, but its normal haunt is the equator. So you see a lot of rainforest, right? South America, Africa, the Congolese rainforest, right? The Amazon rainforest. Here in Sumatra, Indonesia, the Philippines, there's a lot of rainforest, okay? Malawi, by the way, where I did my Peace Corps service, is like right there. That's Lake Malawi. So we were not in a rainforest, but we would get the monsoons. Every year we get monsoons. It's a crazy time of year.
Is it near Kilimanjaro?
It's kind of close. Kilimanjaro's in Tanzania, and Tanzania was our neighbor to the north.
Did you ever go up there?
No, I never went to Tanzania. I went to Zambia, doing some sightseeing, but I never went to Tanzania. All right, so the Intertropical Convergence Zone. This is actually a part of the ocean. It's called the doldrums. Has anyone ever heard of the doldrums? Yeah, have you heard of the doldrums?
Yeah, I was going to sail around the world and study a lot of this.
Yeah.
A place where there's no wind
Yes.
or anything.
Yes.
You have to motor through or
Exactly.
get stuck there.
So I'm so glad that you just said I was going to sail around the world.
Yeah.
That's kind of a unique experience.
Absolutely.
Right, so,
Actually,
and you have to know that, right? You have to know about the doldrums because in the doldrums, again, they follow the ITCZ. So where you get the ITCZ, the wind is the air is rising. So it's not traveling horizontally across the surface so that you can't do sailing there. It's all rising, and because it's all rising, right, the air is converging and rising. Imagine this. So the air is coming, it's converging, intertropical, right? Convergence zone is converging and rising. And because it's rising, you don't get these surface winds to power sailing ships. So that's why they call it, and the doldrums, and so sometimes people say, like, I'm in the doldrums. Have you ever heard anybody say that before, I'm in the doldrums?
Mm-hmm.
Sometimes, I guess it's kind of an old saying, but it means, like, I'm depressed, because this is a really, basically crappy place to be if you're sailing, right?
You're just stuck there.
You're stuck.
You're not moving, period.
Right, so when people were sailing, that was the main method of ocean transportation, it was a really crummy place to be because you were waiting to get through the doldrums and drift through the doldrums because there's no wind. So this is showing the ITCZ during July in red, and like I said, it migrates. Some places, look over the Indian Ocean, it really migrates crazy, right? It migrates a lot. This is the January ITCZ in blue. So you can see how it moves up and down with the seasons, okay? So you can see, like I said, here, Malawi's right here. So our rainy season would be, usually actually the rains in Malawi would start right on Christmas, which is, guess what? That's the winter, right? The winter solstice. And you can see right around the winter solstice, that's when the ITCZ comes right and sits right on top of Malawi in Africa. And that's when you get the crazy rains. And it really is crazy. I mean, it's a tremendous amount of water. Now the biggest rains in the world happen when you get the Indian monsoon season, right? And that's when the ITCZ comes and sits right on top of northern India. And you get a double effect in northern India because you also have the Himalayas right there. And that creates a, has anyone ever heard of like something like a mountain orographic or mountain effect to the rains? So when hot water tries to rise up the mountains cause it to cool, right? Because if the wind has to rise up over the mountains, it's going to lift up and cool off. And that's going to even double the effect of the rising air and the rising cooling air. So there's an orographic effect there too. So the biggest rains we get in the world are right here in northern India during its monsoon season. Okay? So that's what it looks like. And it's true. I mean, it is crazy. In northern India, you get like 400, I think that record is like 428 inches of rain per year. Okay, for comparison, Corpus Christi, we get 33. Average for America is 38 inches per year. So they're like more than 10 times what we get. So it's dumps, right? So that seasonal shift in the ITCZ brings monsoon seasons to India during the basically like the summer, what would be our summer solstice. Okay. All right. So what you're going to see, the first global circulation belt that we have to talk about is the Hadley cell. So number 17, if you flip onto the back now, we got everything on the front page, right? Everything's answered. So the next thing is, what's that name of the global wind cell in which air rises at the ITCZ and descends at the tropics? That is called the Hadley cell, or the Hadley cell. Hadley cell, really, not Hadley cell. Hadley cell. So you can see what happens is that air rises. This is showing the surface of the Earth, right? So here's the equator. You see that, 0 degrees. So here's the ITCZ, which is pretty close to the equator. Okay, and like I said, it migrates north or south. So air is going to rise close to the equator at the ITCZ, right? It's going to rise. Then it's going to go to the north. In the northern hemisphere, it's going to travel to the south in the southern hemisphere. And then it's going to sink down at around this migrates too, but it's going to sink down around at the tropic line, close to the tropic. So it's either going to, and usually it comes down on average around about 30 degrees. That place where the air descends is called the subtropical high. Subtropical high. And it is on average at around 30 degrees north or south. Okay, so it's pretty close to the tropics. Okay, so what is, number 18 says, what is the subtropical high? Okay, what happens to air, again, I keep asking you this question, but what happens to air when it rises? What happens to the temperature of the air? It's rising. And what's going to happen to the temperature? It's going to cool, right? It's going to cool according to the adiabatic cooling rate, adiabatic lapse rate. It's going to cool off. What happens when air starts to sink and descend? What happens to the temperature? It gets hot, okay? Now I want you all to think about this. Pretend for a minute that you're a parcel of air at the equator, okay? So you're just a nice little humid puff of air. You start to rise at the equator because you're hot. And you start rising, and then what happens? You start to cool down, and then eventually you condense, right? You hit the dew point, you start to condense, you start to pour out all of that latent heat, where you release all your latent heat from condensation. You pour out all of your precipitation. So now you're up in the air. You're way up. You're flying really high. Now you're cold and you're dry. Very dry. Why are you so dry now? You precipitated, right? You precipitated. So you're cold and you're bone dry. And now you're going to come to about 30 degrees north and you're going to start to sink. What's going to happen to your temperature? You're going to heat up. and you're going to still be bone dry. So you have these descending hot, dry air descending right about 30 degrees north. And it happens globally. Okay? Now, do you remember when last time we were talking about descending air and pressure systems? So what is that? Do you remember what descending air does to the local air pressure? It rises, right? The air pressure rises, subtropical high pressure. It's talking about the high, it stands for high pressure, not high temperature, it stands for high pressure. So there's a high pressure zone right here at about 30 degrees north. It's hot, it's dry, and the pressure is high. Do you got that? It's hot, it's dry, and the pressure is high. Over here at the ITCZ, it's also hot, but things are cooling down, okay, as it rises. But it's humid, there's a lot of precipitation, and the pressure is low because of the rising air. So there's a band of low pressure, and there's a band of high pressure that forms from this circulation of the Hadley cell. Okay? Everybody got that? So imagine what's going to happen now. You have the see this right here? I don't know if you can see this, but it says equatorial low. That's the ITCZ. So the air is going to rise. It's going to come down at about what's called 30 degrees, which is called the subtropical high. Another term for that is the horse latitudes. Probably, maybe Timmy has heard of that too. Do you ever talk about horse latitudes? No? But I'm sure you talk about the trade winds.
Yeah.
Yeah.
Of course, the trade winds.
Yeah, trade winds are huge in sailing. So they're going to come down. The air is going to rise up at the doldrums, at the equatorial low, the ITCZ. It's going to come up and out, and then it's going to come down at the horse latitudes at 30 degrees north, 30 degrees south. It's hot, dry air, and it's high pressure, okay? And then what's going to happen? So this is a convergence zone. The air is coming in. This is like a divergence zone. So the air is coming down, and it's got nowhere to go. You've got this band of air coming down. It's got nowhere to go but north and south, right? So it's either going to go north or south. Do you see that? Does that make sense to everybody? It's going to try to go north, and it's going to try to go south. But now you tell me, y'all, what happens when air tries to go in a straight line? It always gets deflected. To the right in the northern hemisphere, to the left in the southern hemisphere. So it's going to try to go to the north, but it's going to get deflected, and it's going to go to the right. And it's going to try to go to the south, but it's going to get deflected and go to the right. That creates a very famous band of winds called, now to the south of the horse latitudes, they're called the trade winds. Very, very famous, been used in human history, right, for a long time for sailing vessels. They use this you can imagine this is what they used to cross from Europe to the New World, right? They use the trade winds because they're blowing from the east to the west. To the north, you get the westerlies. And they're blowing from the west, out of the west. That's why they're called the westerlies, from the west to the east, okay? So, gosh, I give you like no room to explain this. I'm sorry. You know what we're going to do? I think we're going to just kind of, I don't really think you need to know anything about, I don't really think you need to know everything about starting at number 24 down. We're not going to cover that, I think. So you can just cross 24, 25, 26, 27. You can cross that off. Because I don't want to cover that. I just want to focus on global circulation belts. So we're cutting stuff out. So hopefully, maybe you could just put, I'm sorry, I don't give you enough room there for number 21 at all. So maybe you could just put a little arrow and answer number 21 somewhere at the bottom. Does that make sense what I'm saying? Because I just don't give you enough room, okay? So I'm saying number 21 says, what are the trade winds? What causes them? And I'm trying to make sure you understand this, because again, this has huge repercussions for ocean circulation. Huge repercussions. So the trade winds originate at the horse latitude. Air tries to move to the south, but it gets deflected by the Coriolis force, and it starts moving basically east-west, from the east to the west. And so you're going to get these west-blowing winds going from about 30 degrees, and they're going to converge there to around the equator. There are these west-blowing winds. Then on the flip side, to the north of the horse latitudes, you get the westerlies, and they're blowing from from the west to the east. They're coming out of the west. Westerlies usually, I don't think they're as important for sailing. Did you ever talk about westerlies? Probably trade winds were.
Yeah, that was definitely something to think about. But I mean, I only soloed and did like a test run on a 30-foot boat, like Lake Eufaula, Alabama, 150 miles down a river to somewhere off at the bottom of Alabama.
Yeah.
And then jumped across the ocean soloed.
Yeah.
To almost to Tampa, but like I was trying to test a 30-foot boat before I upgraded to like 50-foot.
Yeah.
Like if you go across those type of waters, you want a bigger boat that cuts through the waves. Easier, but I mean, it was almost a nightmare when I got in the ocean.
Yeah.
On the boat.
Yeah.
Like, I was like 3 days in a storm.
Yeah.
And soloed.
Yeah.
So I had to stay awake the entire time.
Oh, man.
My motor went out.
Yeah.
So I'm literally sailing on land.
Yeah.
And it was just a logistical nightmare.
Yeah.
Messed up my boat, like completely.
Yeah.
But I mean, it was a good experience.
Yeah.
But no, I was in the horse latitude.
Yeah.
So, and I mean, when you're close to the coast, the waters are really nice and like the best experience in the world. But like, as soon as I got out on the ocean, like things change really fast.
Yeah.
And the waves are massive.
Yes.
Out there.
And we're going to spend a lecture on waves. We're going to talk about why generally you get higher waves in the open ocean, because it's tied to depth. Because the height of waves here close to the coast is limited by the depth of the water. So you can only get waves so high in the Southern Ocean. I showed some videos from the Southern Ocean, and it's just bananas. They have the biggest open ocean waves there.
Yeah, exactly.
Yeah. So I was going to ask if you ever sailed in the Southern Ocean.
No, I was planning on it, but
Yeah.
I needed a bigger boat before I take it.
Yeah.
To me, it's risk management.
Yeah.
And everything has to be right, or I'm not going to do it.
Yeah.
So I need a big boat with all kinds of different backup systems.
Yeah.
So I didn't have what I had.
Well, I'm very glad you're in this class to share these experiences, because it's very pertinent.
Yeah.
Yeah.
I've done a lot of crazy stuff. So.
All right, so number 22. I know it's a little bit hard to see, but hopefully you can see the map. Hopefully on number 22 you can see the equator, right? I hope you can see the equator. Let me put number 22, the map I use, up on the board so you can kind of look at it. Oh wait, I don't know if I want to do that because I'm going to interrupt the owl. But I'll forget it. But do you all see the equator on number 22, the map? Okay. You all following me? You see the equator? Okay. The line of latitude, the next line of latitude that's shown, those are 30-degree marks. Okay? Those are 30 degrees. So those are basically the horse latitudes. So you're supposed to draw in the trade winds, the westerlies. I'd also like you to draw in like the PGF. So the PGF would be like, that's the pressure gradient force, right? So the pressure gradient force, oh, this thing is totally dead. The pressure gradient force coming off the 30-degree line, which is the horse latitudes. would just be straight north-south, right? So what I want you to draw is just arrows straight north-south coming out of the horse latitude. And that's the PGF, the pressure gradient force. But then the actual wind direction, right, gets deflected to the right. And that's due to Coriolis force. So that's kind of what I'm trying to get you to draw on your little map there. Does that make sense to everybody? Does anybody want me to check their thingy, their map? Eliana, should Yeah, that's right. Yeah, you got the westerlies, you got the trade winds. So if you want to come up after class and have me check your map or something, I can check it for you. So I want you to get this because it's very, very important for the rest of the class. Okay. All right, so we got the rising air at the ITCZ, descending air at the STH. That's the Hadley cell. That's the most important global wind belt in this class. Now there are two others. They are of secondary importance. They're not as important. There's the Ferrel cell, which starts at 30 degrees and ends at 60 degrees north or south. And then there's finally the polar cell, and that starts at 60 degrees north-south, ends at the pole, comes down at the pole. So there's actually a high-pressure system always hanging out at the pole, North Polar. So Santa Claus is always going to have high pressure in his area, because it's always going to be coming down right there from the polar cell. Okay, so there's the Hadley cell. Okay, I just kind of liked this diagram I found online, right? Because it's showing the temperatures, how the temperatures are changing too, right? You start off hot at the equator, the air starts to rise, it causes the precipitation. Notice that it cools down as it goes up. Then that cold air starts to descend, and notice that at 30 degrees north, the air that's coming down, it's hot now. It's heated up, and it's also dry. Okay, now, as air gets compressed, so the air that's descending, it's experiencing an increase in pressure. Remember, because when you heat up, when you descend, you're going to be going to higher air pressures. Just like an airplane descending from high altitude to low altitude, you're going to, you know how your ears pop, right? And you're on an airplane, you're going from high altitude to low altitude. It's from the pressure changes, okay? That's going to cause the air to heat up. Has anyone ever done this before with a bike pump and going like pumping air with a hand pump into a bike tube? Have you ever noticed how it literally gets kind of hot? Like the pump actually gets hot? Well, if you do it really hard, I promise you'll notice this. I used to just think it was because I'm like, pumping on it really hard and it's warming up, maybe because of my hand or the friction or something. But it literally will get hot. The pump will get hot as you pump air. If you ever have I remember I had a guy talking about, like, he has like a big, he worked in industry somehow, and they have these big industrial air compressors, and they get really hot, like the fittings get very hot. And that's because the air is getting compressed, okay? So air, as it descends, because the pressure increases, it's going to heat up. So the air is descending at the subtropics. It creates a lot of warm, dry air. So this creates what are called subtropical high deserts. So if you take a look at the deserts of the world, this is just a map of deserts of the world, you might notice that a lot of them are kind of focused on the horse latitudes. So the Sonoran, the Chihuahuan deserts, those are very close to us here in Texas. They are at about 30 degrees north, approximately. Okay, the Sahara Desert, it sits right there, focused on 30 degrees north, right? All the deserts in the Arabian deserts, right, in the Middle East, 30 degrees north is about, right? Now, the ones in like the Gobi and Asia, those aren't subtropical high deserts. They happen for different reasons. The Simpson Desert in Australia, again, same reason, 30 degrees south. The Namib and Kalahari deserts in the south of Africa, again, they're subtropical high deserts. And part of the Atacama, now the Atacama Desert in South America happens mostly because of rain shadow effects, because of the Andes Mountains, but there's some subtropical high desert action going on there too. Okay, so the air that's coming down is hot and dry, and that's what creates these deserts. Right, there's the 30-degree horse latitudes put in for you. Now I want you to take this back to what you've learned before in this class. I don't have any questions, so I don't have any questions about this. You'll notice on the assignment, but it's very important. So I want you to I want you to make this connection here. If I had more room, I would have put questions about this. But this is a map showing evaporation compared to precipitation. Does everybody remember seeing this in the past? I've shown it actually maybe 2 or 3 times in the past. So it's a map of actually backwards, precipitation minus evaporation. Okay? You'll notice that right around the horse latitudes, you get a lot of evaporation, right? So we get more evaporation here, more evaporation here, more evaporation here. In the Mediterranean, Red Sea, right? Persian Gulf, more evaporation. Okay? That's due to the subtropical high, that descending air. You might remember back we talked about salinity, and salinity patterns, global salinity patterns of the surface ocean is very difficult to understand. And just now in this class, you're going to start to hopefully be able to understand those patterns. So I'm going to show a map of that in a little bit. Notice though that around the equator, we get precipitation outpacing evaporation, right? And that's because that's where the ITCZ hangs out, and it creates a lot of precipitation. So you see right along the equator, we get in relativity a high level of precipitation versus evaporation. Okay, does everybody see that? What I'm talking about? See, now if you didn't know anything about these cells, about these circulation cells, you would probably just assume that you get the most evaporation at the equator because it's hottest, and you get more and more precipitation as you go to the north or to the south. But that's actually not true, and it's not true because of these cells, because of the Hadley cell, the different circulation cells. So 30-degree latitude, these are called the horse latitudes. I'd love to know why they're called the horse latitudes. I don't know why. It's a good question. So the air is coming down, descending right around 30 degrees north, 30 degrees south. Okay. So this would be these little arrows I'm showing right here would be like the PGF, okay, the pressure gradient forces that arise from the descending air around the horse latitudes. And then these blue arrows that I've drawn in here, those would be like the actual wind direction because it gets deflected to the right in this northern hemisphere and to the left in the southern hemisphere due to Coriolis force. Okay, so what do you call these winds? This right here. What do you call that wind belt right there? That's moving from the east to the west. Trade winds. And what do you call these ones up here? Westerlies. Okay. So the westerlies and the trade winds. So this is showing kind of like the average winds, how they're moving over the globe, okay? And you can see that you got the trade winds blowing east to west. That's shown in the yellow. The blue are the westerlies. Okay, you see those westerlies. We see in the southern hemisphere. Notice that I want to point out something to you. Notice that the trade winds of the south are blowing in the same direction. Right, so that doesn't, I know how like a lot of times when you look at the south, things flip, but it doesn't flip here. They blow in the same direction. Same with the westerlies. So the westerlies are still called the westerlies in the south. They're still blowing, out of the west. So that's why doesn't change the name. And now I want to point something out to you too. This will come up later in the class. Do you notice how in this band where the westerlies are blowing, there's not much land at all? Okay, this is the Southern Ocean. Remember I was talking with Tim just a few minutes ago about how the Southern Ocean has the biggest waves in the open ocean? It's because of this. Look how little land there is in the Southern Ocean. So these westerlies just blow around and around and around and around and around. They just go forever. See, here you have a problem because of the Siberia, right? Russia is right in the way, so it blocks it. But these just blow around and around and around, and it creates these huge waves because it basically has an infinite fetch. We'll learn about that later in the class. Okay. So there are these two other convective cells, the ferrule cell and the polar cell. I want to point something out to you. Also, you might have seen before. You probably heard of the jet streams, right? Have you all heard of jet streams before? So jet streams are actually created by this same process of these convective cells, global convective cells on Earth. So where you have the Hadley cell circulating like this, and then you have the ferrule cell circulating in the opposite direction, it basically creates like an eddy right there, this long streaming eddy, because you got something going like this, right? And so right in the middle between them, you have this eddy, and that's the jet stream of very fast-moving air. Okay. So and that affects. I just kind of want you to be aware of these things because it becomes important later when we talk about El Nino. Y'all heard of El Nino? Okay, so it becomes important later when we talk about El Ninos and like how El Ninos change global weather patterns. Okay, so it's because jet streams, where the jets. You ever hear this? Like people talking about the weatherman talking about this, about where the jet stream is, and oh, the jet stream's kind of like the polar jet streams. Maybe it's like dipping a little bit further to the south, and it's going to bring in like colder air, and blah 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 blah. So that's why I want you to be aware of these things because the location of these jet streams play a big role in affecting our weather and our climate. Okay. So there you go. This is just a little GIF showing these global circulation patterns. I think it's pretty cool. Hopefully that all makes sense to you now. Okay. One last thing I wanted to touch on, and then I'm going to let you all go for today, because I know that we've been like going right to the minute for the last few lectures, so I want to let you out a little bit earlier today. But last thing I want to touch on today are land breezes and sea breezes, and the reason I want to talk about this particular subject, it doesn't really relate too much to the rest of the class, but I kind of want to talk about it just because we get a lot of this here in Corpus Christi, so it's kind of like a local issue that I want you to just have some understanding about, because maybe you've wondered, like, why do we have so much wind here? It's a very windy place. They set up all the windmills. It has a lot to do with this whole phenomenon of land breezes and sea breezes. Okay, so you know that living next to the ocean, we often get a sea breeze. Okay, and that's usually that water is a little bit cooler than the land, and hopefully you understand that by now because we've talked about that a lot about why the ocean does not heat up as quickly as the land does. Good final exam question. We've talked about that many times now. So the air that comes up off of the ocean is going to be very humid. It's going to be very wet. It's going to have a lot of humidity, but it's also going to be cooler. Okay. So it comes up off of the ocean and goes inward. So why does it do that? Well, as you know, I've shown this slide like 5 times, I think, in this class. So starting to get the sense it's important somehow. But as you know, the water does not cool up. The water does not heat up as quickly, so it stays relatively cool relative to the land during the day. But think about this. The opposite happens at night. The land cools off more quickly, and the water, because it has that high heat capacity, retains its heat. Has anyone ever like, maybe it's kind of probably you've experienced this before if you've ever waded around in the bay at nighttime. I don't know if anyone does that. Maybe I'm kind of creepy wading around the bay at night. No. I do it for flounder. That's why I do it. But sometimes you go in there and it's like the water's like nice and warm, It's nice and warm. It's cold out, but it's nice warm water. And that's because why? Because the water has high heat capacity, right? So it retains its heat from the day. It holds on to it. It's got the high heat capacity. And so the opposite effect happens during the night. During the night, the water sometimes can be warmer, actually generally is warmer than the land. So during the day, the land is hotter, and the water is cooler. During the night, the water is warmer, the land is cooler. So that the fact that there's like a thermal difference there, a thermal gradient, I can say, is going to create some wind and some air motion. Okay. So basically, what happens is that you got the very hot land during the day. It heats up and it starts to do what hot air does. What does hot air like to do? Rise, right? So hot air likes to rise because it becomes more buoyant, because it's less dense. So it rises, it convects, it goes up, and it will go over the cooler water, cool down, and that's what, and it'll cool down and come back to, because you're actually creating a low pressure system here, right? If you think about this, you're creating, when air rises, it creates a low pressure system. So that'll make this land with the convecting, rising air relatively low pressure, and this place where the air is descending relatively high pressure. And so remember, high is always going to move from high to low, or at least it's going to try. It gets deflected, of course. But these are relatively regional, or like local effects, regional effects, so they don't get affected by the Coriolis force as normal. But so we're getting this circulation pattern that's going to bring like a cool breeze into the land, and that's of course what kind of cools off the land near the coast and helps us to have a more like even temperature compared to like San Antonio, where they're far away from the land, so far away from the water. That'd be weird. You're far away from the land. I'm getting all tongue-tied today. And so that's what helps to keep the temperatures relatively cool. The opposite happens though during the night. So actually what often happens is that the direction of the wind will reverse during the night. And you'll get the land being relatively cool, the water now being warmer. It's going to rise, come up, and it's going to sink down and cool. Okay? And that's part of the reason too. You can think of, you know, sometimes we get like really foggy mornings, right? Because you can think about all during the night, you get this warm, moist water, right? Well, I guess water is always moist, but you warm, moist air over the water, going up, coming, and then sinking and descending over the land. It's bringing a lot of moisture in, right? And so that's what always keeps our humidity levels pretty high here in Corpus Christi. But anyway, that's a little bit about what creates the wind patterns that we see here in Corpus. Okay. That's all I'm going to talk about today. You can just cross off, like I said, number 24 to 27, and go ahead and you can leave. If you would just leave lecture assignment number 16, make sure you turn that in today. And then lecture assignment 17, you can have more time to work on it. And if you would like me to look at your map, I can look at your map after class. But besides that, have a good weekend, and I'll see you on Monday.